last class we had talked of spatial enumeration or spatial occupancy enumeration. Okay, and we said that one of the simplest ways of enumerating space, let's say a two-dimensional space, using a set of squares, is by dividing the space into an array of cells and then having an x by y array of zeros and ones which tells us whether a particular cell is occupied or not. Okay, if we use a mechanism like this, then let us say if we have a resolution of x in the x direction and y in the y direction, we need space which is equivalent to x times y. And even if let us say our object is something like this, then a portion which is let us say a large portion which is totally outside the region that we are trying to model, or a large portion which is totally inside, even that portion will get enumerated or will get divided into cells. Okay, so this is quite inefficient, and especially if you extend it to 3 dimensions, then we will need an array of a size of x into y into z, then it can become very inefficient. So in order to take care of this, one method that is used is what is called a chord tree. Okay, this is a technique which is used to model, let us say, 2-dimensional surfaces. For 3 dimensions we will go on to Octrees, we will come to that. So for a 2-dimensional surface, if we have an area like this which has to be modeled, we will first divide this into 4 regions. Okay, let us say this is our region number 1, 2, 3 and 4, and this region, if it is, let us say if our figure to be modeled is something like this, okay, this is the region I am trying to model. Then we see whether each region is inside or outside. Okay, if you look at this region, we cannot decide whether it is totally inside or totally outside. If you look at region number 2, that is totally outside. Similarly, region number 3 is totally inside, and region number 4 is again partially inside and partially outside. Okay, so for region number 2 we will store a 0, for region number 3 we will store a 1. Okay, and when we consider region number 4, we will divide it further into 4 parts. Okay, so if I divide region number 4, we will get, let us say, parts like this. Now this region number 1 is now divided again into 4 parts. Let us number them 5, 6, 7 and 8. 5 is totally inside, so that gets a 1. 6 gets a 0 because it is totally outside. 7 gets a 1 and 8 gets a 1. Okay, similarly if I consider region number 4, I will again divide this region number 4 into 4 parts, because region 4 is partly inside and partly outside. Okay, so let us say this becomes something like this. Okay, after 8, let us say this is 9, 10, 11 and 12. Okay, again region number 9 I cannot decide, but 10 is totally outside, so 10 I will give it a 0. 11 again I can't decide, 12 also I can't decide. So again I will take 9 and divide it into 4 parts, and we continue this way. Okay, and the way we will represent this is in the form of a tree. This
you might never reach a situation in which
I'll come to that.
Indefinable accuracy.
I'll come to that, please. Okay, so let's say this complete region is represented by one root level node. Okay, this is being divided into 4 parts. Okay, this is region 1, 2, 3 and 4. Now for region 1, we haven't been able to decide, but region 2 has been given a 0 because it's totally outside the region that we are trying to model. Okay, so for region 2 I give it a 0. Similarly, region 3 I have given it a 1. Okay, and then region 1 I am again dividing into 4 parts, and region 4 also has been divided again into 4 parts. Okay, so region 1 is divided into 5, 6, 7 and 8. 5, 6, 7 and 8, and 4 is divided into 9, 10, 11 and 12. Okay, now again 5 has been given, let's say 1, and 6 is given a 0, and 7 and 8 have been given a 1 each. Okay, so between 9, 10, 11 and 12, 10 is given a 0, the other 4 are again divided further. Okay, and so on. Okay, so at every node, let's say this is my node number 0. At every node we are dividing a space into 4 parts, and each part we are trying to say whether it is inside or outside. Okay, and this way we can continue till the whole of a solid or the whole of a area has been marked with zeros and ones, or till, let's say, some portion, let's say if I divide this 12 further, now this portion is totally outside, this is also totally outside, but let's say this portion is again partly outside and partly inside, but now I might decide that this is too small a portion to be considered. Okay, so I will neglect this portion. Okay, so we decide upon a criteria as to how much of area is being lost. Okay, how small is the portion that is being lost or gained. Okay, for example, in this I might decide I will consider this to be totally inside. So this area I will give it a code of 1, this one. Okay, so we will decide upon an accuracy level, and according to that we will give zeros and ones to every region. Okay, so our area that we are trying to represent will not be modeled accurately. It will model only up to the accuracy that we desire. Okay, and larger the accuracy that we want, the more the number of times we will have to subdivide the area. If you want a very accurate model, let's say if you want to go up to microns, okay, then we will have to keep subdividing up to a large extent. Okay, which means that the depth of the tree will become very large and the space involved will also become very large. Okay, and if you consider square that is being represented at this level, let's say if this has a size of 1, okay, unit size, the size here will be half, the size here will be 1/4. Okay, because we are dividing a square into 4 parts into 2 equal parts in either direction. Okay, these 2 parts are going to be equal. So the size of the square here will be 1/4, the next square will be 1/8 and so on. So depending on the accuracy that we want to go up to, the depth of the tree will depend on that. Okay, so the depth and memory space they will both depend on accuracy. Okay, the other thing that is important in this is that, let's say in this region I want to model a curve which looks like this. Okay, that means I want to model, let's say, this area. Okay, I'll start by subdividing this into 4 parts. Again I'll subdivide this, subdivide this, subdivide this, okay, and then possibly subdivide this way, and so on. Okay, and finally I get a representation which is something like this. Every node is divided into 4 parts and so on. Okay, but now the mathematical equation of this is lost. Okay, let's say this is maybe an arc of a circle. From this representation, it is very difficult to say that this is an arc of a circle. Okay, because now we only have a set of zeros and ones which define the different cells. Okay, the whole thing is represented by a set of zeros and ones like this, and so on. Okay, this is, let's say, 1, this is 0, 0, 1. Okay, now from this data it is very difficult to find out what is the equation of the curve. Okay, so in a pure quad tree we say that the geometrical equation or the equation is of boundaries is lost. Okay, that is one big disadvantage of this. We don't know what will be the equation, governing the curve, the bounding curve. Okay, some of the advantages of this model are, let's say if I have an area which is like this, and I have another area, okay, which is, let's say, something like this. Okay, and we want to find out, let's say, the union or the intersection. That can be found out very easily. Okay, because every cell I can see whether it is a 0 or a 1 and decide about the about whether it is going to be included in the final area or not. Okay, so the algorithms for union and intersection will be very simple. Okay, but again the time that these algorithms will take, that will depend on the resolution that we have chosen. Because if we have chosen a very fine resolution, my algorithm might still take a very long time because I have divided into very small cells. So time involved might be large, but the algorithms are going to be very simplistic. Okay, so we say Boolean operations can be implemented easily. Okay, if you want to compute the geometric properties, that is, let's say, the area of this region, I only have to take the area of each of the individual cells and keep adding. Okay, if I look at this tree, the area at this point is 1, the area of all nodes at this level is going to be half into half, which is 1/4. The area of all nodes at this level is going to be 1/16. Okay, similarly if I want to compute the moment of inertia, that can also be done because I know each cell whether the area exists there or not. Okay, so the properties of this area can be computed easily. Of course, we can't say anything about the time. We can say something about the time only if we know the resolution. If the resolution we are looking for is very high, then the time involved will again go up. But the algorithm will be simple because no two areas have any portion in common. If you take this cell and this cell, they are disjoint. Okay, if you remember earlier I had mentioned that if you say the volume of A union B is equal to volume of A plus volume of B minus volume of A intersection B. if I consider any two cells in a quadtree representation, the area of A intersection B will always be 0. Okay, so we only have the area of A plus area of B, or moment of inertia of A plus moment of inertia of B. Okay, so properties can be easily computed. Okay, so these are some of the advantages and disadvantages of this method. The biggest disadvantage is that if the accuracy is large, we need a lot of space, and that the geometrical definition of the boundaries is lost. Okay, this is the biggest disadvantage of this method. Okay, any questions regarding this? The other thing is, let's say if we want to display so an area which has been represented like this, for a two-dimensional object, display can be done very easily. I just have to start drawing each of the squares when they are 1. If I look at this tree, whenever a leaf node is a 1, I can draw that square. If it is 0, I can omit it. Okay, if we do that, we will get a display which would, for a curve like this, my display might look something like this. It won't be accurate. Okay, even portions which are outside the curve, they will be shown as inside. Okay, because I have my curve, instead of looking like a smooth curve like this, will look stepped. It looks something like this. It won't look like a smooth curve, it will look stepped like this. Okay, because you have divided into a set of squares. Okay, and if you look at the boundary, the region around the boundary is divided into smaller size cells, and the regions which are away from the boundary, they are divided into a larger size cells. Okay, but if we have a very complex boundary, okay, which has a lot of details, in that case we need to go into very small size cells. Only then we can represent the boundary accurately. Okay, because accuracy at the boundary is always lost in these methods. Okay. Now, if we want to model a three-dimensional solid, okay, so far we are talking about modeling of areas, two-dimensional areas. If we are talking about 3D solid, then we extend the same thing into an octree. Okay, this tree was called a quad tree because every node had 4 children. Okay, every node had 4 children, so it was called a quad tree. Okay, now if we go into 3 dimensions, instead of talking of a unit square, we will now talk of a unit cube. And this unit cube will divide it into 8 portions. We'll have, let's say, 1, 2, 3, 4, this one will be 5, this is 6, 7 will be at the bottom corner, and this one will be 8. Okay, these are faces of 2, this is 4, this is 6, and this is 1. Okay, so every cube will be divided into 8 octants, and the tree that we have, every node will have 8 children. Okay, so if this is my root node 0, it will have 8 children, 1, 2, 3, 4, 6, 7 and 8. And each of these nodes will be either a 0 or a 1, or it will have again 8 children after that. Okay, so this way, this is a simple extension of quad trees into a 3-dimensional space. Okay, in 2 dimensions we had 4 children for every node, in 3 dimensions we will have 8 children. Okay, essentially what we are doing is in every dimension, in the x direction, let us say this is the y direction and the z direction, we are dividing the unit length into 2 portions. Okay, this is divided into 2 portions here, 2 portions here and 2 portions here. So we get 2 cube, that is 8 parts of a cube, and similarly in a 2-dimensional space we got 4 parts. Okay, so for a 3D object we get an octree, and this octree will have the same properties as a quad tree. Here also the depth and memory will depend on the accuracy. Here also the geometrical equation of the boundaries will be lost. Okay, the Boolean operations can be implemented easily, because for every cube, for every cubic cell, it is either a 0 or a 1. So if you are computing the union, that can be done easily. Okay, and properties can be easily computed. So I want to find out the volume, I only have to traverse the tree and I will get the volume. Similarly, if I want to get the moment of inertia, I only have to traverse the tree and I will get the volume. Okay, for a tree like this, for all the leaf nodes, we will compute the property, either the volume or the moment of inertia, and add it up. Okay, so that can be done quite easily. Okay, any question about quad trees and octrees? Any question about solid modeling? Okay, if there are no question, I will wind up now, and if you have any questions we can discuss that right now, otherwise I will wind up the thing.
So what model does Unigraphics use?
Unigraphics is using basically a combination of CSG with BREP. Okay, it has a graph based model for the primitives, plus it is using a set of Boolean operations. So actually if a model is using an octree representation, then that can be seen very easily. I mean the display that you will get will have jagged edges and you will see small cubes and so on. Okay, because one normally does not like to go into a very high resolution in the case of octree representation. One thing, the display using octree models, okay, that can be quite simplified. Okay, depending on of course the technique that one uses. If one wants a good rendered image with the nice shading, then it is not going to be very good, because let us say, okay, I think I should mention that if you have a cuboid like this which has been divided into a very high resolution and so on, and you want to find out the surface normal at any point, that is not going to be easy. Okay, because the geometric equation is lost. Normally if you have a, let us say, a 3-dimensional surface and you want to find out the surface normal at any point, you can compute the derivative in one direction, derivative in a second direction, and take the cross product. You will get a surface normal. Okay, but if you have a model represented in octree representation, getting a surface model is not very easy. What the best that can be done is you draw each of the cubes independently. So the surfaces of the cube which are visible, you keep drawing those surfaces one after another. Again, once you have a good enough representation, you stop. Okay, so that is the way display is normally generated.
CSG always has to have a model internally to operate, to evaluate.
Yes,
to
yes,
operations.
yes.
So are these two the only alternatives, the BREP and Octree?
They are the commonly used alternatives. Yes, you have some variations of BREP. Okay, but they are essentially all graph based. You have some kind of adjacency information being represented. Okay, strictly speaking, in the BREP, the complete model is represented as a union or intersection of half spaces. Okay, so let's say if you want to represent a cube, so represent the equation of each of the faces and then say which half space is inside the solid, and the intersection of all of those will give us the final solid. Okay, but some kind of graph based representation is always used in which adjacency information is being stored. That is the most commonly used form of thing. Each of these representations, whether it is brep or a pure CSG or octree, in some situations one is helpful, in some other situations the other is helpful. Okay, and quite often one keeps switching from one to the other. You have algorithms available for getting the octree representation of a brep model. Okay, or a octree representation from a CSG model of simple primitives, and the other way around. Okay, so such in fact some algorithms are also available for getting the equation of a model represented by an octree model. Okay, because that is quite commonly needed. So algorithms are available, but they are complex. Okay, they will do some kind of a fitting between the cuboids, each cuboid being a 0 or a 1. They will do some kind of a regression technique and get a equation of a curve, but it is complex. Okay, so between these three techniques one can switch from one to the other, but at the cost of time. Okay. Patron. Patron is essentially a pre and post processor for a finite element analysis module. Okay, so it doesn't have extensive solid modeling capabilities.
Sir, in this model, the Octree model, so if you want to, there will be a problem if you want to zoom in. Like we can only
in Octrees.
Because we have already defined the level of accuracy, and if you want to zoom in, then won't we have problems?
See, depending on the accuracy, you are storing the model depending on some accuracy. Okay, the display is depending on some other accuracy. Okay, so if you want to get a display which is finer than your stored model, that is not going to be possible. Okay, sometimes what I have also done is that the equation is stored, the equation of all the surfaces is stored, and then when you want to use that and you need the Octree model, you generate the Octree model immediately. Okay, so that you don't lose the geometric information also. In that case, you are using a combination of two, some kind of a boundary representation plus an Octree. Octree used only when you need the Octree representation. Okay, any other questions? Okay, in that case, I'll call it a day now.